In this video, I'd like to talk about finding relative extrema by using derivatives. The first thing we're going to talk about is what we call the first derivative test. This test says that if c is a critical number of f of x and the sign of the derivative changes from positive to negative at c, then f of c is a relative maximum. So let's look at this graph. I've kind of set up the situation. We've got, it kind of looks like a parabola-shaped graph, but oriented upside down. If we look at, I'm going to say a derivative on the left-hand side, we can see that the derivative there would be positive, versus if we look over here on the right-hand side, we can tell the derivative there would be negative. And so somewhere there was a change in sign, then that meant that there's going to be a relative maximum at the critical value f of c. And then, so on this particular one, c would have occurred in this region somewhere. And so right there, we'd have a relative maximum. Now remember that critical numbers must be in the domain of f of x, and that's important for this particular test. Okay, the second part of the first derivative test states that if c is a critical number of f of x, and the sign of f prime of x changes from negative to positive at c, then f of c is a relative minimum. On there, looking at this graph, it looks like we have a parabola-shaped graph oriented upward. And so if we look at the derivative on this side, we can see we have a positive type derivative. I'm sorry, negative type derivative. If we look at the derivative here, we can see we have a positive type derivative. So somewhere in between those x values, the sign of the derivative changed. And so on this particular example, c would be down here in this region somewhere. And so that would make that value there a relative minimum. And then the third part of the first derivative test states that if c is a critical number of f of x and the sign of f prime of x doesn't change at c, then f of c is neither a relative maximum or minimum. So just because we have a critical value doesn't always imply that we're definitely going to have a relative max or minimum. Sometimes the sign can't change. So we look at this first graph, we can see there, if we're looking at derivatives, it looks like we're going to have positive derivatives. And then someone here, we're probably going to have a derivative of 0. But then up here, we have a derivative that's also positive. So basically had positive values of derivatives on this side, positive values of derivatives there. Somewhere in here, we would have had a critical value c. If the sign didn't change, then we're not going to have a relative max or min at that point. All right, we can see on this other graph that we've got a negative slope on this side. Somewhere in the middle here, it looks like we'll have a 0 slope. And then over here, once again, we're back to a negative slope. So we went from negative to negative as far as the sign of the derivative. In here somewhere would have been my critical number. So once again, I didn't change sign of the derivative across the critical number. So that means there's no relative maximum or minimum. In general, a relative maximum or minimum means that relatively speaking, there's either a high or a low. So on this very first example, we can see that relatively speaking, that this would be a high point. I'm going to say relative to what's around it. And then here, this would be a low point relative to what's around it. All right, so on here, what we're going to do is just look at some examples. For this particular function, they want us to find the requested information. And on here, I'm going to zoom out a little bit so that we can see our notes. Down on the bottom here, it's asking for domain, critical numbers, where it increases, decreases, and then any kind of local max or min. And local max and mins are the same thing as relative extrema. And on those, you always want to give a y value for your answer. But also, a lot of times, they'll ask for the x value that goes with it. And so on there, there's the list of things that I want to determine for this particular problem. So the first thing we're going to do is go ahead and make a note of the domain. So we know that this is a polynomial function, and so the domain would end up being all real numbers. And what I'll do is I'll go and copy all these answers down into our blanks at the end of the problem. Okay, so we've got that taken care of. The next thing is we want to find critical numbers. To find critical numbers, I know I need to find a derivative. So I'll do f prime of x and then take a derivative. Here, if I multiply the power of 3 in the front, we'll have 2/3 multiplied by 3, and then reduce that power by 1, so it would become squared. This derivative would be negative 2x, and then this derivative would be negative 24, and then derivative of negative 4 is 0. Okay, from here, simplifying that, We're going to cancel these 3's. And then if possible, we'll see if we can factor our derivative. So we have 2x squared, and then minus 2x, and then minus 24. We notice that all those terms have a factor of 2 in common. So we'll pull out that factor of 2. That leaves an x squared minus an x, and then minus a 12. That's a trinomial that will factor further. So x and x is the first two factors. And then here we want factors of negative 12 that will add or subtract to the understood negative 1 in the middle. So that would be a negative 4 and a positive 3. And then notice when we multiply negative 4 and positive 3, we get negative 12 at the end. All right, for critical numbers, we find those. And I'll go ahead and label. If you're on an exam and doing a problem, especially as lengthy as this one, you want to label what you're doing. So critical numbers I find either from setting the derivative equal to 0 or finding out where the derivative is undefined. So that's my thought on this particular piece. For this one, because I have a polynomial derivative and it's in factored form, I'm going to go ahead and take that factored form to find out where the derivative is 0. So we have 2 times x minus 4 times x plus 3 equal to 0. The 2 in the front, I'm going to say we don't have to worry about because it doesn't have a factor of x with it, so you're not going to get any values from that. On this one, if we set that equal to 0, we're going to get x equal to 4. And then on this one over here, if we set that equal to 0, we're going to get x equals to negative 3. Now, because our domain was all real numbers, then those two are critical numbers. All right, on the next thing I had to think about, finding out where f prime is undefined. Because my derivative is a polynomial function, there's not going to be any values for which the derivative is undefined. So we've got our critical numbers here being x is 4 and x is negative 3. All right, now the next thing to ask for was increasing, decreasing behavior. And on that, we're going to do a number line test with our derivative and our critical numbers. And so on here, we're going to do the critical numbers in the order in which they would come on the number line. So we would have negative 3 over here somewhere, and we'd have 4. And then what I did before is kind of put a dotted line just to visually separate. This does not mean asymptotes or anything like that. It's just visually separating the number line so that we can see it. And then we want to choose test values between each of the critical numbers. So over here, I could choose, say, negative 4 as a test value. In between negative 3 and 4, I could choose 0. And then to the right, I could choose a 5. All right, from here, we have to remember to put those test values into the derivative. And all we care about is what the sign of the derivative would be. So on there, what I'm going to do is I'm going to go to the factored form of my derivative. That's the easiest form at this point for me to work with. And I'm going to plug my test values into that factored form and determine the sign of the derivative. So f prime at negative 4, this would be positive 2 times negative 4 minus 4 times negative 4 plus 3. All right, positive 2 is definitely positive. Then when I multiply, or when I add negative 4 and negative 4, that's negative. And then when I add negative 4 and 3, that's also negative. So I end up here with, do this, I just want the signs here really. So I end up with a positive multiplied by a negative. That's going to be negative, multiplied by negative. Another negative is positive overall. So what I would want to see on a test is I would want to see the sign of the derivative, and then I also want to see the behavior as far as increasing, decreasing. So that would indicate to me that I'm increasing in that interval. Now go and do f prime at 0. So 2, and then here 0 minus 4, and then 0 plus 3. 2 is definitely positive. When I do 0 minus 4, that's going to end up being negative. When I do 0 plus 3, that's positive. So essentially here I'm multiplying two positives and a negative, so that would end up with a negative. So derivative is negative. That's saying I'm going downhill. And then f prime at 5. We have 2 times 5 minus 4 times 5 plus 3. 2 is positive. 5 minus 4 is positive, and 5 plus 3 is positive. So we have 3 positives being multiplied, which would definitely be positive. So the sign of the derivative is positive, and then that would indicate to me that I'm increasing. Now, this does actually 2 things for me. I just tested to see where my function was increasing and decreasing, but I'm going to say for free, I have now determined using the first derivative test where I have relative max and mins. And so in this particular problem, notice that we went from, I'm going to say, going positive slope to negative slope. That's going to indicate here that that value is going to be a relative maximum. So I'm going to go ahead and put that as a note. We have a relative max by the first derivative test. And then over here, we went from decreasing to increasing. That's going to mean that value there is a relative minimum. So in testing for increasing, decreasing behavior, we also use the first derivative test with my number line test to determine where I have relative max and mins. Now, -3 and 4 aren't my relative max and mins. Those are the x values that would, I'm going to say, determine my max or my min. All right, so what I'm going to do from here is go back and I'm going to say before I answer my question about increasing, decreasing, I'm going to go ahead and determine my relative max and min. And the way you do that is you always go back to the original function. So in these particular problems, you're using your derivative when you do your number line test, but when you're trying to figure out relative max and mins, you always plug the critical numbers at which they occur back into the original function. Okay, so for that particular one, and you can use a calculator here, and I'm just going to go back and kind of copy. So we're going to have a relative maximum at x equals -3. Go back to the original function and evaluate it at -3. The original function was 2/3, and then it was x to the third, so this would be -3 to the third power, and then minus -3 to the second, and then minus 24 times -3, and then minus 4. And on something like this, just plug all of that into your calculator. In this particular situation, you're going to get 41 as that y value. So you're going to say that we have a relative max of y equals 41 when x is -3. Okay, so when we talk about a relative max or min, always give me a y value, because that tells me how high or how low that relative max or min is. Okay, we also had a relative minimum at x equals 4. And so on there, evaluate the function at 4. So 2/3 times 4 cubed minus 4 squared minus 24 times 4, and then minus 4. Using our calculator there, that one's going to give you an ugly type fraction. If you need help with your calculators as far as making sure that you're able to get a fractional result out instead of a decimal, just let me know. You can also use Google. Google the type of calculator that you have and then tell it that you want an exact fraction answer, and you should come up with a video that will show you how to do that. On this one, we get -220 divided by 3, and you can just leave it like that. If you need, I'm going to say, a decimal answer for homework, you could definitely do that. For me, on a test or on a quiz, leave it as an exact, and that will be what I want. So here you would say I have a relative minimum of y equals -220 over 3 when x is 4. All right, I think we have everything we need except for increasing, decreasing, and we can look back up at the test. I'm going to say our test number line up here to see that. So let's go ahead and come down below and fill in our answers. Our domain, we said from the beginning, was all real numbers, so -infinity to positive infinity. The critical numbers that we got were x equals -3 and x equals 4. Okay, as far as increasing, decreasing, let's go back up to our number line test. Okay, we can see that we're increasing on this interval here and that interval there. Remember that these are always open intervals and they're always, I'm going to say, reliant on our critical numbers. So we'd say we are increasing from negative infinity to negative 3 and then also from 4 to infinity. So there, negative infinity to negative 3 and then do union 4 to infinity. And then decreasing, we can see that we were decreasing on the interval between negative 3 and 4, since the derivative was negative. So negative 3 to 4. Once again, all of those are open intervals. And then local max of, I believe we said 41 was the y value, and that was at x equals negative 3. And then we had a local minimum of negative 220 over 3 when x was 4. All right, that particular example I wanted to consider since it was polynomial. Polynomial functions have certain behaviors when you look at their relative max and mins. All right, so now what I want to do is I want to switch gears and I want to look at a rational function. So on this particular rational function, we want to make a note first of the domain. So I'm going to come up here and say, let's make a note of the domain. Okay, in a rational type function, we know that the denominator can't be 0. In this particular example, we can see that x could not be equal to negative 1, because if it were, it would make the denominator 0. So that would mean that the domain is negative infinity all the way up to negative 1, exclude that, and then do union negative 1 to infinity. So essentially it's all real numbers except for negative 1. Okay, so then you want to find critical numbers. To find critical numbers, we need to take a derivative. So f prime of x, because this is a quotient, we're going to use the quotient rule. So quotient rule says keep the denominator, and then take the derivative of the top, which would just be 1, and then minus, keep the top, and then take the derivative of the bottom, which in this case is also 1, and then all of that is over the denominator squared. All right, from here we want to see if we can simplify this derivative as much as possible. Okay, here we're distributing a negative. The 1s aren't really making any difference. So we have an x plus 1, and then minus an x minus a 2, and then all over x plus 1 all squared. That's ultimately going to lead to the x's there are going to cancel out or 0 out. And then we have a 1 minus a 2, so that'll be a negative 1 over, and then an x plus 1 all squared. So there's our derivative. Okay, to find critical numbers. So now I will label. Okay, I'm worried about either where the derivative is 0 or where the derivative is undefined. In this particular example, because it's a rational function, finding where the derivative is 0 is going to say go to your derivative and set the numerator equal to 0. Well, on this particular problem, if we set the numerator equal to 0, the numerator is negative 1. Negative 1 is not equal to 0, so doing that doesn't make sense. So that's out. All right, for finding where the derivative is undefined, if you have a rational function, that means essentially you're going to set the denominator equal to 0. However, we have discovered that you don't have to actually set the entire denominator equal to 0. You only have to set, I'm going to say, the factors equal to 0. So on this one, we have that x plus 1 factor in the bottom. So that would be x plus 1 equal to 0. That would give me x is negative 1. Now, to be critical number, you have to be in the domain of the function. And notice that we said that negative 1 was the one thing that x couldn't equal. And so on this, we would say no critical numbers, because that x equals negative 1 is not in the domain. Now, knowing what we know about, I'm going to say rational functions, if we have factors that don't cancel, and those factors get left in the denominator, those factors, I'm going to say, basically give us vertical asymptotes. So we're going to make a note up here that we actually have a vertical asymptote at x is equal to negative 1. Now, what that means for us is we don't have any critical numbers, but we do have a vertical asymptote. And so when we go to do our number line test, we're going to put that vertical asymptote on the number line, and we're going to denote it as such. So it's not a critical number, but it is something that we want to consider. So what we'll do there is I'll put the little dotted line to just separate, but I am going to clearly mark it as, hey, it's a vertical asymptote. The reason for doing that is if it's a vertical asymptote, it can't possibly yield a relative max or a relative min. So the behavior of the derivative may change across that number, but because rational functions aren't defined at their vertical asymptotes, it can't possibly yield a max or a min. So we want to be careful. All right, as far as test values, let's say to the left over here, let's do -2, and maybe to the right, let's do 0. Okay, and then we're testing those values back into our derivative. So f prime at -2. So there I'll have a -1 over -2 plus 1 all squared. The top value is going to be negative no matter what, since it's -1, and the bottom value is actually going to be positive no matter what, since that whole group is squared. So a negative divided by a positive is a negative. So there, the sign of my derivative is negative. That's going to indicate to me that I'm decreasing. F prime at 0, just worried about the sign. We have -1 over, and then 0 plus 1 all squared. We have the same situation as before. We have the negative on the top, positive on the bottom. That would result in a negative overall. So we have a negative here, behavior there also decreasing. Now, there are situations that you're going to run into where the behavior there changed, and that's what I'm talking about of being careful that we don't say a vertical asymptote is a relative max or min. So normally a behavior change will indicate that, but not when it's a behavior change over an asymptote. All right, so from here, I think we've got all that we need. We can say we don't have any relative max and mins because the only place that it could have occurred was at an asymptote, and it can't happen there. And then I believe we've got everything we need as far as increasing, decreasing behavior as well. Okay, so on this one, I will make a note. There are no relative extrema. All right, and then we're going to come down below and go ahead and fill in our answers here. We said domain was everything but -1, so -infinity to -1, and then union, -1 to infinity. Critical numbers, there were none, and on a test, I'd want you to say that. Okay, increasing, I was increasing nowhere. So if I look back up here, I was decreasing over my domain, but increasing nowhere. I'd also want you to put that. All right, I was decreasing everywhere in the domain, so that left out that -1. So we would say there, -infinity to -1, and then union, -1 to infinity. All right, and then here we didn't have any relative extrema, so what you could do on an exam is you could just kind of bracket that off and just tell me there's no relative extrema. And you're getting credit for telling me that because you've done the work up above, and I'm going to say it's just as important to say that there are none than there is to say, you know, if there are actual values there. All right, so far we've looked at a polynomial function and we've looked at a rational function. All right, so now what I want to do is kind of shift gears and I want to look at something that's a combination of functions. So in this one, we've got some things that look like polynomials, like the x squared and the -3, but then we also threw in this exponential function. All right, so on this, the first thing I want to talk about is the domain. I'm going to say from algebra, we know for polynomials, the domain is all real numbers. We also know that for e to the x, based off of the graph of e to the x, so your e to the x graph ends up looking something along these lines. Let me make this a little cleaner. And so looking at a graph of e to the x, then we can see the domain there would be all real numbers. In the way that this particular function is combined, because we don't have, I'm going to say fractions where you have x's in the denominator or something under an even root, something along those lines, nothing bad is happening with this particular function. And so on this one, we'd be safe to say that our domain is all real numbers because of the nature of the functions that we're actually combining. So we could say negative infinity to positive infinity there and be good for the domain. All right, so now we need to find critical numbers. So to do that, we're taking a derivative. So f prime of x. So this first piece we have to be careful about because it's actually a product. This last part over here we don't have to worry about because we know when we get to the derivative of that, that actually is just going to be 0. So on this one, we're going to use product rule. So we keep the first function, and then we take the derivative of the second. There's two things you can do at this point. E to the x, as far as a derivative, is just e to the x. Or you can use our three-step approach where you're saying that the derivative of an exponential is the natural log of its base, the function itself, and the derivative of the exponent. Normally by this time, when we get to an e to the x and we're saying what's its derivative, we're just going to say it's e to the x. Right? Plus, for the second piece, you're going to keep the second, and then you're going to take the derivative of the first. All right, and then as we mentioned earlier, derivative of -3 is just going to be 0. Now from here, what we want to do is factor. We notice that these two factors share definitely an e to the x. They also share a factor of x. So we're going to pull out an e to the x times x. And you can put those in any order. And then that would leave us left with an x plus 2 on the inside of that group. All right, so now on critical numbers, we're trying to figure out where the derivative would either be 0 or where the derivative is undefined. So here, finding where the derivative is 0 would basically mean set each factor that involves an x equal to 0. So that would mean that e to the x times x plus 2 is 0, which would mean e to the x is 0, would mean x is 0, or x plus 2 is 0. All right, e to the x equaling 0 does not yield a solution, and we can do this in one of two ways. We can know that looking at our graph, for the graph of an e to the x function, we actually have a horizontal asymptote along the x-axis, which means that it would never cross the x-axis in this particular situation. And so there's no values of x that would yield a y of 0. The other way we could do it is to solve an exponential function, you actually take the natural log of both sides. And if we took the natural log of both sides, if you did natural log of 0 on your calculator, then on that particular one, you're going to end up yielding an error message. Okay, so this particular piece has no solution. The best way at this point to remember is just say, hey, I know e to the x can never equal to 0. Okay, x is 0, that's actually already done, so that's going to be a critical number. And then here we're going to have -2 as the other critical number. Now, 0 and -2 are in the domain because we said the domain was all real numbers. All right, so at this point we'll go and we'll do our number line test with -2 and 0. So here's -2. Here's 0, and we're going to separate those off. Neither one of those are vertical asymptotes, so we don't need to mark them as such. Okay, then from there we want to pick test values. So let's try, let's say -3 here. Between -2 and 0, let's do -1. And then to the right of 0, let's do 1. All right, so now we test those values in the derivative to find out what the sign would be. So f prime of -3, that would be e to the -3rd, and then times -3, and then times -3 plus 2. All right, all we care about is the sign of the result. E to the -3rd, we notice from the graph that the entire graph is up above the x-axis. So it doesn't matter what power I put in, e to a power will always be positive. Okay, obviously -3 is negative. And then -3 plus 2 is going to end up being negative. So I have a positive multiplied by 2 negatives, that would end up being positive. So in this region, my derivative is positive, which means I'm increasing. All right, now do f prime at -1. So that'll be e to the negative 1, and then times negative 1, and then negative 1 plus 2. As mentioned before, e to any power is going to end up being positive. Negative 1 is obviously negative, and then negative 1 plus 2 is going to end up being positive. So we have two positives multiplied by a negative. That would end up being negative overall. So they are negative, and then that would indicate to me that I'm decreasing on that interval. All right, and then the last one, I'm going to do f prime of 1. So f prime of 1, e to the first. Here, this would be 1. This would be 1 plus 2. E to any power is positive. 1 is obviously positive, and then 1 plus 2 is positive. So there we get a positive overall, and then that would indicate that I'm increasing. Now, because negative 2 and 0 weren't any kind of asymptotes, then they could possibly be extrema. We see because of our behavior that negative 2 is going to end up being a relative max. I went from going uphill on one side to downhill on the other. And then we're going to see 0 is going to be a relative min. On that one, I went from going downhill on the left to uphill on the right. So by the first derivative test, I'm able to determine those two relative extremas. So let's go ahead and write those down, what they're going to end up being. So we had the relative max at negative 2. We have to remember that negative 2 is not the relative max. That's the x value for which it occurs. So now to actually find the relative max, we go back to the original function and we evaluate it at x equals negative 2. So doing that, we're going to say f of negative 2 equals be negative 2 all squared e to the negative 2 and then minus 3. Okay, and I'll show you here what I want just as an answer. If they want a decimal online, you could definitely type it in your calculator and get a decimal. On here, negative 2 squared is obviously 4. The e to the negative 2 power is multiplied by that. So what I'm going to do is write it as an e to the positive 2 in the denominator under the 4, and then minus a 3. And that's fine for me. I'm going to want an exact answer. That's an exact answer. All right, so we're going to say there's a relative max of y equals 4 over e squared minus 3 at the x value of negative 2. All right, and then for the relative min, we know there's a relative min at x equals 0. So if we evaluate the original function at 0, we're going to have 0 squared times e to the 0 minus 3. E to the 0 is 1, 0, 0, or 0 squared 0, so we'll have 0 times 1 minus 3. So that'll be 0 minus 3, just negative 3. So we're going to have a relative min of y equals negative 3 at x equals 0. All right, so let's see if we're ready to fill in all our answers down below. So on this one, we had a domain of all real numbers. We had critical numbers at x equals 0 and also x equals negative 2. On the number line test, we can determine increasing, decreasing behavior. For this one, we can see we're increasing from here all the way to that critical number, and then also all the way there to that critical number. So that looks like negative infinity to negative 2, and then union 0 to infinity. All right, and then I'm decreasing between the two critical numbers, and we could see that from the graph up above. So between negative 2 and 0, we can see we have a negative behavior with my derivative. And then here we found out we had a local max of 4 over e squared minus 3, and then that was at x equals negative 2. And then there was a local min of negative 3 at x equals 0. All right, so what I'd like to do now is I'm going to look at one more, I'm going to say more complicated rational function, and then we're going to look at an application to wrap this up. All right, so this particular problem, I'm going to say it's not as simple of a rational function as we had before. Okay, this particular one, we might want to consider factoring it. I don't know if that's something that we'd want to do. I think that considering we're asking for a domain and we're wanting to know if there's possibly any vertical asymptotes, that factoring would be a good thing to do. We know that sometimes there's holes left where factors cancel, and so that wouldn't be a vertical asymptote. We see here if we were to factor, we could use -3, -3 as factors of 9 that would add or subtract to -6. And then on the bottom's already factored. Thinking of it in that way, we can see that whatever value would make the denominator 0 would for sure be a vertical asymptote and not a hole. So on here, that will help us determine our domain. So by the way, if you did have a hole, you would still want to consider, I'm going to say, that hole as being somewhere you couldn't have relative max and mins. So on this one, we're going to say domain would be everything except for what would make the denominator 0, which would be 7. So there's that. All right. And then from here, we want to take the derivative. Now, in taking the derivative, I'm going to use the original form of the function. So f prime of x equals, we would start with the bottom, x minus 7, and then derivative of the top, so 2x minus 6, and then minus the top, times the derivative of the bottom, which would just be 1, and then all of that is over the denominator squared. All right, from here, I'm going to go ahead and distribute, and I'm going to be really careful. On the first part, I'm actually going to FOIL. So this is going to be FOILed out. And then on the second part, we're seeing we're multiplying by 1 here. That's not going to make a difference, but we do have this negative that's going to need to be distributed. All right, so here we're going to end up FOILing 2x squared, and then minus a 6x, minus a 14x, and then plus a 42, and then distributing the negative, negative x squared plus 6x minus 9, and then all of that is over the x minus 7 all squared. Right, and then we're wanting to combine like terms. So on here we've got a couple of x squareds. We got a 2x squared minus an x squared, so that would just be x squared. We've definitely got a batch of x's. We have a couple of x's that would cancel. We have the negative 6x and the positive 6x. That would leave me with a negative 14x. And then we have the 42 and then minus the 9, so that would be a 33. Now all of that is over x minus 7 all squared. Now, if we can, we'd like to factor. So in the numerator of this, we're going to see if that will factor or not. And then the bottom part's already factored for us. Okay, we need factors of 33 that would add or subtract to 14. So we're going to put x and x in the first slots, and then it sounds like we can do a 3 and an 11. Both of those negative to give me the negative 14 in the middle, but the positive 33 at the end. And so in this one, we've got the factorization. All right, now we're going to go to critical numbers. All right, so on here for the critical numbers, we're wanting to know where the derivative is 0 or where the derivative is undefined. And I'm going to make this short and sweet. The derivative would be 0 where the top is 0. It looks like on this one, the top would be 0 at either x is 3 or x is 11. The derivative would be undefined where the bottom is 0. That would happen when x is 7. Now, as far as critical numbers, we want to make sure that all these are actually in the domain. So we look back up and we remember the domain was everything except for 7. So the x equals 7 is not in the domain. So these are our only two critical numbers. Okay, and we'll make a note, not in domain. Okay, now when we do our number line test though, all three of those are going to go on the number line. So let's go ahead and do that. Okay, be careful here that we're doing these in order. So 3 would be left, 7 would be in the middle somewhere, 11 off to the right. We're going to separate these out. When we get to the 7, we're going to put a big note that says, hey, this is a vertical asymptote. That means it couldn't possibly be a relative max or min, even though the behavior might change over that particular value. Okay, now we're going to test values into the derivative. So let's choose possibly 0. Let's choose 4, 8, and 12. And plug those into the derivative. Okay, the derivative, the easiest form there is this factored form. So that's the place I'm going to plug these test values into. So f of 0 will be 0 minus 3, and then times 0 minus 11, all over 0 minus 7 squared. We notice that the bottom part is squared, so no matter what, it's going to be positive. On this one, on the top, we have a negative multiplied by another negative, so that's going to end up being positive. So positive over positive, positive overall. We've got increasing behavior there. All right, the next one, f prime at 4. So there we have 4 minus 3, 4 minus 11, and then all over 4 minus 7 all squared. Bottom is positive no matter what since it's squared. 4 minus 3 is positive. 4 minus 11 is negative. Here this is going to be negative overall. So negative and decreasing. All right, f prime at 8. So 8 minus 3, 8 minus 11, 8 minus 7 squared, 8 minus 3, positive, 8 minus 11, negative. Bottom positive no matter what, that will end up being negative. All right, and then the last one, f prime at 12. Okay, so 12 minus 3, 12 minus 11, and then 12 minus 7 all squared. We're going to get a positive times a positive over a positive. So positive overall there. So positive value there. That would mean I'm increasing. All right, so on here, before I actually go down to the final answers here, we can see that we've got a couple of relative extremas. We've got a relative extrema at this critical number, because you see us going from, I'm going to say, increasing to decreasing. So that's going to be a relative maximum. And then over here at the critical number of 11, you see us going from decreasing to increasing. So that's going to be a relative minimum. Okay, so I'm going to kind of shortcut here on those, and I'm going to go ahead and just find the y values, and then we'll put it in the proper notation down below. Now, on these, remember that we're plugging the critical numbers of 3 and 11 into the original function to find the relative extrema. So let me come over here, and I'll do that right quick. So relative extrema, we know that there's going to be a max at 3. So a max, x is 3. And if we go stick into the function, we're going to have f of 3. And you can either plug into the original function or the factored form of the function. It doesn't really make a difference. I'm just going to plug back into the original function. So on that particular one, we're going to have 3 squared, and then minus 6 times 3, and then plus 9. And then all of that is over 3 minus 7. Okay. And you can do that on your calculator. On this particular one, you actually get 0 when you do that on your calculator. And then there's going to be a min, specifically at x is equal to 11. If we plug in 11, we'll have 11 squared minus 6 times 11 plus 9 all over 11 minus 7. Plugging into your calculator there, you're going to get 16. All right, so now let's go down and fill in our answers. So for this one, we had said that the domain was everything except for 7. because 7 was a vertical asymptote. All right, for critical numbers, we said that for our critical numbers, we got 3 and 11 only. 7 was not in there. So x equals 3 and x equals 11, but not 7 since it was not in the domain. Okay, for increasing, decreasing, let's go back up and look at our chart. Looks like for increasing, I'd be increasing all the way from negative infinity all the way up to 3, and then also from 11 to infinity. So for that, let's see, negative infinity to 3, and then union 11 to infinity. All right, for decreasing, we've got to be a little bit careful. We see that we're decreasing all the way from 3 to 11, but there's a vertical asymptote at 7, so you want to make sure you leave the 7 out. Don't just say from 3 to 11. You're going to have to union 3 to 7 and then 7 to 11 and leave that 7 out. So from 3 to 7 and then union 7 to 11. Okay, and then local max, the max actually was 0, and that was at x equals 3. And then the minimum was actually 16, and then that was at x equals 11. All right, so the last thing I actually want to do is go through an application problem. And in the application problem, it's asking us something about a minimum. And so this is going to be where we're now applying these things that we've learned about finding relative max and mins. All right, so on here, the first thing I want to talk about is the domain of this particular function. It says that suppose the cost function of a product is given by c of x equals this function. We notice that it's a polynomial function, which generally would mean that the domain is all real numbers. But because it's tied to an application, sometimes there's restrictions. It says find the production level, in other words, the value of x. Remember here that x is going to be a number of items. Well, it doesn't make sense for x to be a negative amount of items. So we can basically think of x values as being anything from 0 on to infinity. So the domain of this function, because of the application that's tied to it, would be 0 to infinity. And we're going to say we can allow for the 0 to be included. All right, they want to ultimately find the production level value of x that's going to produce a minimum average cost per unit c of x. And remember that average cost means you're going to take the cost function and you're going to divide by x. So I'm going to put that as a recall. So c of x with the bar on the top, that means average cost, and it's found by taking the cost function and dividing by x. Let's go ahead and do that for this particular example. So on the top, we're going to have the cost function that they gave us, and then in the denominator, we're going to divide by x. Now we can rewrite this, and basically, because there's a single x in the bottom, take each term in the top and put it over the single x. So we can split it. So 0.003 x cubed, that term over x. Keep whatever sign is next in the top, so plus, and then 9x over x. And then plus 9610 over x. And the reason I'm doing this is here in a little bit, we're going to want to take a derivative. How do I know that? It's asking me for a minimum. If it asks you for a max or a min, you're going to take the derivative and you're going to perform a first derivative test on it by using a number line and testing. So I'm wanting to make this average cost function as pretty as I can as far as taking a derivative. Notice at this point, I can then use exponent rules to cancel some of these x's. So here I've got a single x on the bottom that would cancel with a single x on the top. That would leave me with 0.003 x squared. Here I have a couple of x's that would cancel. That would leave me with just a 9. And then on this one, I can't take the derivative of something that looks like that at the moment. We know that there's an understood 1 on the exponent that we have in the bottom. I'm actually going to rewrite this one using a negative exponent so that I can use the power rule when I take a derivative. All right, so now we're going to want to find our critical numbers. To find the critical numbers, we need to take the derivative of the average cost function. To do this, as far as notation, put your average cost function inside of a group of parentheses, and then you can put the prime on the outside of that. All right, taking the derivative of that average cost function, you're going to multiply the 2 to that decimal in the front. That's going to result in a 0.006, and then we would reduce that power to an understood 1. Derivative of the 9 would be 0, and then the derivative of that next piece, you'd multiply the negative 1 to the front, so that would give you negative 9610, and then if you reduce that power by 1, it'd give you a negative 2 power. Now, this is a tricky thing as far as a derivative. This is not a polynomial derivative because of the negative power on the x. So we're going to actually want to rewrite this as a rational function. So on here, I'm going to use my exponent rule to make that exponent a positive exponent by dropping it down to the denominator of that piece. So I'll do negative 9610, and then I'll put the x squared in the denominator. And then we haven't run across a problem like this so far, in that we now need to find a common denominator so that we're able to find critical numbers. So if we have something that's a polynomial function, we can generally factor and then set each of those those factors to 0. But when it's a rational function, we need to be able to find critical numbers by setting the numerator to 0 and the denominator to 0. And at this point, we have a combination of those two. We have a piece at the front that's polynomial, that 0.006x, and we also have that rational. So this needs to be combined together in one piece. Let's put this over 1, and then we're going to do a common denominator. Common denominator would be x squared, so we would need to multiply the top and bottom of this function by an x squared to get that common denominator. So doing that, that's going to result in a 0.006, and then we have an x times an x squared, that'd be x cubed, all over x squared, and then minus 9610 all over x squared. So now we have a common denominator. Go ahead and shove these two fractions together over one single denominator. All right, and then we have our, I'm going to say our rational function in the proper form to be able to find critical numbers. Now on this one, for the critical numbers, we're not going to worry about factoring. Our numbers aren't nice, and there was nothing simple to factor like an x squared out of the top, anything like that. So for the critical numbers, we're going to say worry about either where the derivative, and on this case, we're doing this notation for our derivative, is 0, or where that derivative is undefined. Okay, finding where the derivative would be 0 would mean setting the top equal to 0. So 0.006 x cubed, and then minus 9610, set that to 0. Okay, and we're going to solve this one by taking roots. We have that x cubed that we're going to ultimately need to get rid of, so we'll take a cube root at some point. At this point, I'm going to add over that 9610 to the other side. All right, and then in doing that, we can now divide by the 0.006. All right, and then here we're going to get an ugly decimal. So what we'll do, I'm going to go ahead and write as much of that ugly decimal out as my calculator gives me. On this one, I get 1601666, and then as far as decimals on the calculator, it ends up being repeating, so it's actually 6 repeating from there on out. Now, on the calculator, I have to take a cube root. Some of our calculators won't do cube roots, so what I'm actually going to do is raise both sides of this to the 1/3 power. So raising it to the 1/3 power would cancel the 3 and the 1/3, and it would accomplish the same thing as taking a third root. The only thing you're going to have to be careful of is that you make sure you put that 1/3 power in parentheses when you actually do it on your calculator. So this would be x, and then taking the 1/3 power of this, you would get 117.0013068. Now at this point, I am going to round this. So in this particular problem, it's wanting to find a production level or a value of x. This is a critical number, so this is going to be, I'm going to say representative of number of items. So I'm going to go ahead and round at this point and say x would approximately be 117 items if this is going to be an answer. So this will be my critical number for setting the derivative to 0. Okay, finding where it's undefined, that would be where the denominator is 0. So that would be x squared equals 0. Well, the only way that x squared is going to be 0 is if x is 0. Now remember, 0 is actually in my domain, but it's an endpoint of my domain, so I have to be a little bit careful there. So now let's go to a number line and test my critical numbers and around my critical numbers. So on the number line, I'm going to do something tricky over to the left that we haven't done before. And I'm going to say right there, we're actually going to cut it off, and we're cutting it off at 0. And 0 was one of my critical numbers, but there's not going to be anything to its left. Okay, my other critical number was 117. I'm going to be a little bit careful there when I choose my test values. The 117 is slightly rounded, so I'm going to make sure that I stay far above and far below that value. I'm not really close. So in other words, if that's rounded, 118 or 116 would probably not be good numbers for test values. I want to make sure that I get entirely above that value. Here, what I'll do to the right is I think I'm going to do 120, and that will get me far enough to the right that I won't have any kind of problem because I rounded. And then what I'm going to do over here is do 1, because that's between 0 and 117 and definitely not close to 117. So what I'm going to do now is take those values and plug into my derivative. Now on here, the derivative was ugly. I didn't simplify it, so I'm expecting to totally plug these in my calculator to determine if the sign of the derivative is positive or negative. So notationally, I would do C bar of 1, and then the derivative notation here. And then I'm plugging in. So 0.006, 1 cubed, and then minus 9610. And then all that is over 1 squared. Type that in your calculator. The only thing you care about is the sign. Now, when you do type this in your calculator, if you use, I'm going to say, your calculator to do the whole entire process together, make sure to put parentheses around the numerator so that that piece is done properly as far as order of operations. Doing this, you get a negative result. Okay, for the second piece, you're doing the derivative. So the average function derivative evaluated at 120. Right, same thing, if you plan on typing all of this in your calculator at once, make sure to put extra set of parentheses around the top. Doing that, you end up with a positive result. Okay. So in here we had a negative, which means I was decreasing. In here we had a positive, which means I'm increasing. Now go back and remember what this question was asking for. It wanted to know a minimum. I would have been in trouble in this particular situation if I had been increasing between 0 and 117 and decreasing to the right of 117. That would have yielded a max, which is definitely not what I'm looking for. So I'm relieved in this particular situation to see that I'm getting a relative min at this 117 value. Okay, so that's what it's asking me for. It's not asking for increasing, decreasing, anything along those lines, but it's wanting the value of x that's going to produce the minimum. They're not even asking for the minimum. Okay, so on this one, I've got what I need. I've got my support. I've got the graph that shows me it is a minimum. So on this one, all I need to say is so x equals, and what you could do is say approximately equal to 117 produces, and I would want a word answer here. So produces the minimum cost per unit. All right, if you have any kind of questions, make sure to let me know.